David Lewis, 50 year higher level maths, 3D problems, 2 specifically pyramids. In the last video we learned that when we are looking at a 3D problem we want to turn it into a 2D problem. How we do it is we draw the piece from above and then we try as best as possible to draw in the shape or the triangle that we are dealing with. Pyramids can be a little bit trickier, so there are 2 types of pyramids we need to be aware of on our course. A pyramid with a square base and a pyramid with a rectangular base. Now the examiner will obviously make that quite clear to you, or in a question you will see that, but always look out for that. Don't just automatically assume it's a square or a rectangle and vice versa. What's going to happen in here as well is we're going to be looking out for Pythagoras, which is great. Potentially Pythagoras could go over twice. They're going to cross each other, so when they cross each other they actually cut the diagonal lines in half, whether they look like it on my piece or not. And it's also worth noting that in a square all the sides are the same, whereas in a rectangle we have the opposite sides are the same. Now the pyramids that we have to look at, the points at the very height of the pyramid, the apex of the pyramid, is always going to be above the center of the base. So it's always going to be directly above the center of the base. If you envisage my marker being a pole going up to the very, very top of the pyramid, that's it there. So therefore it's going to create right angles. And not only is it going to create right angle triangles for us, but those right angle triangles every single time, instead of being dealt with something on the side like we saw before, are going to be involved with half of that diagonal there. And we get that half diagonal the exact same way you think you would. You don't do anything weird here. What you just do is you do a little bit of Pythagoras, and then when you get this, you just divide it by 2. Okay, so on page 54 of your notes, it says pyramids can be a bit trickier to work with. There are 2 very useful pieces of info to remember, and these are the pieces of info. I put a star beside these. The tip of the pyramid is called the apex. Apex is virtually above the center of the base. Okay. Some student dropping a plug there. Okay, and then it says the center, a line from the center of the base, the apex, is always perpendicular to the base. And then part 2, the center of the base is the midpoint of the diagonal. So basically exactly what I explained there. But knowing those 2 pieces of information will help you out. We're only going to look at 2 questions. 7.6 first of all. It said the pyramid shown below has a square base P, Q or S. Now I have about a 5-6 minute break in between these videos. It's actually as long as I want. And I spent a long time trying to draw that pyramid, and then eventually I just rubbed it out. So you're going to work out from the pyramid from the diagram there, because I tried to draw it on the board and it genuinely, I don't know, it didn't even look like a cone. I don't know what it was. So have a look there, but it says the pyramid below has a square base. Now I'd underline just for the first number of these that it has a square base, and then I'd also go back into reflex mode, it has a square base. So I would draw that square base straight away. Draw it as if you've got some sort of laser vision that you can look through the pyramid and just draw the square base. So we've got P, what are the sides there? P, Q or S. So P, Q or S. And all the same stuff still applies. The point at the top of the pyramid, X, is directly above Y. Now they don't have to tell you that, but because it always is, which is the center of the base. So if we find the center of the base here, the point of the pyramid is directly above that. The vertical height, XY, is 24 centimeters. XY is 24, so there's Y in the center. So if you think of the top of my pen being X, being the very point of the pyramid, that marker is 24 centimeters. Okay. Then it says the slant height, so the height on the outside of the pyramid, the slant height, PX, is 26. Now, all of those slant heights are going to be the same. All of those in this square pyramid here. Okay, so that's fantastic. So the slant height is 26. Grand. Now I've drawn this. There's nothing there that I can really talk about to begin with. But then it says find PY. So find PY. Find this distance. And from that square, for the first time, I'm not able to do anything. So from the base, the first time, I'm not able to do anything from it. But I do have some other information. As you can see from your diagram, they have actually drawn the right angle triangle with PY in it. So it looks something like this. We've got the slant height, PX, grand. They told us that was 26 in the question. We have the vertical height, so which was the height of my marker, so that's XY, which they told us was 24. Connecting that up, we can go ahead and get PY. Now for probably the the 8th time in this set of videos. Is it a right angle triangle? Yeah. We've got two sides looking for a third, so it's Pythagoras. Now don't make the mistake, as we mentioned before, let's just call this something completely different from in the question. Let's just call this A. But let's not make the mistake, it's not A squared equals to 26 squared plus 24 squared. Remember, Pythagoras is C squared equals to A squared plus B squared. C is the side across from the right angle. So we have 26 squared equals to 24 squared plus A squared. And if you put that into your calculator, bring it across, tidy it up, you find out that X, or A, sorry, in this case, is equal to 10. So A is equal to 10. Great, so that we found Py. Now if you wanted to write that in up here, that's probably not a bad idea. So that's 10. Part 2 says find angle XPY, XPY. So quite like our other question, where we were dealing with a cuboid, now we just have to find this angle in here. I'm not going to draw the triangle up again to waste our time. We know A is now 10. We got that in the last part of the question. We're spoiled for choice. We're looking for an angle in SOHCAHTOA. It doesn't matter which one you use. I used sine just because I'm more used to sine. So I call it the sine of B. So you can call that whatever you want. I'm going to call it B now. The sine of B is equal to, remember, the opposite over the hypotenuse. So 24 over 26. If you inverse sine both sides, you'll find that B, the angle you're looking for, is 67 degrees. And that's angle XPY. Again, angle XPY. So at the part in the middle, if you want. Okay, great. So not a big deal so far. And then part 3 says, show that PQ is 10 root 2. Again, I would much prefer if the examiner worded this as find PQ, because then at least we kind of know where to go. Giving you a little bit of a hint, it's something really, like giving you the answer kind of is worse than giving you a hint. It's not, it just confuses students. So show PQ is 10 root 2. So if we go back to our original diagram up here, we know that this is 10 root 2, but I can't actually just say, oh yeah, it's 10 root 2. So I'm going to call it, let's just go with, we've got y's and stuff in here, let's call it C. Okay, so I'm going to find C there. And the only thing that I'm aware of in this case is that that's 10. We've got PY as 10. But because we know in a square base that those diagonals are going to bisect each other, cut them in half, I know as well that all these pieces are the same, almost like the radius of a square, but not a radius. But I know if that PY is 10, well then QY is 10. So if I just take that out there, if I take that idea out, these are all actually right angle triangles as well. So if I take that idea out and I look at this right angle triangle that I have, I am looking for PQ, which we've now called C. Okay, so there's C. I know this side is 10, and I know this side is 10, and we've got a right angle in between all of those pieces there. Okay, how do I know that? Well, if you either know, or if you think about in geometry, it's just if there was a circle around the middle there, that'd be 360 divided by 4 is 90, but that's also just a junior cert theorem. So if we go ahead to try find C, now we've got C squared equals to 10 squared plus 10 squared. So C squared equals to 200, and I would just fully cheat here. Probably shouldn't say that, but I would just write down, they've told us what the answer is, I'd just say C equals to 10 root 2. However, if I was to show you this property, we're going to say C equals to root 200. Okay, you can split root 200 into root 100 by root 2. And root 100 is just 10. So therefore, I can say that this C, or what did they call it in the question, PQ, is equal to 10 root 2. We've proven it there. Okay, so that's the first pyramid one there. Not that big a deal, as long as we know square base and what's going on with that base. Question 7.7, the reason we are doing this is to add one more string to your bow, one more tool to your mathematical toolkit. It's actually a favourite of Rob, this next formula. It's not technically on the Leaving Cert course, but you can use it and it saves you a serious amount of hassle, as you'll see now in a second. So question 7.7, It says, the Great Pyramid at Giza in Egypt has a square base. Again, don't just assume it's a square, let's just check. And 4 identical triangular faces. So each one of the faces on the sides of the pyramid are the same. They're the exact same because it's a square. The base of the pyramid has sides 230 meters in length. Great. And the vertical height of the pyramid is 146. So quite identical to this question, however, just slightly different numbers. The vertex, or the apex of the pyramid, is directly above the center of the base. Okay, cool. And then there's a beautiful picture of the pyramid in Giza there. I've actually been there. Just in case you're wondering, you're sitting at home wondering, yes, he has been there. What are we going to do here? 3D piece, I'm going to draw from above. Okay, so would you believe that? So drawing this from above, we've got question 7.7. Drawing this from above. So I'm just going to call them different names here. So drawing this from above, usually the examiner would give you the different pieces. They would say, like, you know, as we have over here, P, Q, or S. They haven't here, but just for my own sake, I'm going to do it. I'm going to just call the bottom A, B, C, D. What information have they given us? Well, they said we've got 230 on either side, and I'm fairly sure that something like that's going to come into play, so I'm going to put that down. What else do we have? Well, they've actually drawn a triangle in there for us as well. Okay, so that triangle has the going into the middle there and up. So we can say, what is the triangle there? Let's just say it's AO. So let's call this middle part O. So AO, right angle triangle going up, and we said the vertical height means going straight up. That means right angle triangles is 146. Okay, so that's fine. So I've done that before I've even read the question. Right. Find the length of one of the slanted edges of the pyramid. Okay, so find the length of one of the slanted edges of the pyramid. Well, this is a combination of our last 2 classes now, isn't it? Combination of one of our last 2 classes. So we've got to find this. So let's just call it X. That's what we have to find. But I don't have enough information. But if I had this part here, well, then I'd have enough information. So, can I get that part? Well, that part is part of the base, which pretty much always is. But it's AO. How do I get half? Oh, how do I get half of the diagonal? I literally get the diagonal and I half it. So, in that, as usual, a right angle triangle. If I take that out, I have A, C, B, 230, 230. Do some Pythagoras to find, let's just call this Y. So y squared, or AC squared, equals to 230 squared plus 230 squared. So we use some Pythagoras. And y equals to 325.3. Now that's not what I'm looking for. That's not what I put in there. That would be a slip and an error. We only want this. And that, as we know, is half what we've just found there, half that diagonal. Why? Well, because that's what happens in squares. They get bisected by those diagonals. So if I divide that by 2, y over 2 is equal to 162.7. That 162.7 goes in here. And again, we're going to use some Pythagoras, and you can find out that x squared equals to 146 squared plus 162.7 squared. Tidy that up, and x is 219 meters. I bet you didn't think that Pythagoras would be this important, and SOHCAHTOA would be this important, and right angle triangles this important back when we were doing sine and cosine rule, but as you can see, evidently it is. That's actually all we are doing. Okay, and then part 2, the final new tool, the final new thing that you'll need for trigonometry in terms of these practical questions. Part 2 says, find the total area of the 4 triangular faces of the pyramid. So find the total area. Okay. Now, all those triangular faces are the same. So if I get one of them and I multiply by 4, that's the question done. But how do I get one of them? What do I have in terms of the triangular face? Well, I have the base since the very start. So since the very start, I've had that the base is 230. Great. In the last part of the question, it took me a couple of steps, but I found out that the slant heights of these faces is 219. Now they're all the same, so that's the face of the pyramid. If you can imagine the rest of it coming down the back there. Okay, but that's the face of the pyramid. Okay. Well, what can I do? Well, we could go the long method. Because if we were trying to find the area of a triangle, we would have half AB by the sine of C. And that's fine. We have two sides and an angle in between it. So if we use the cosine rule, on this piece here and found one of these angles, then we could go ahead and get the angle and stick it in here. Currently, as it stands, there's no angle. It's not a right angle triangle, so we can't use SOHCAHTOA. But you could do that, definitely, 100%. Another way you could do it is you could drop a perpendicular line from the top. So perpendicular means straight down. Drop a perpendicular line. That's going to form a right angle triangle and cut this in half. And from that, you could go ahead, so you could go perpendicular line. Fine. We could go ahead then and use SOHCAHTOA. And then from that, we would get one of the angles and we could stick that into the half AB by the sine of C. So that's not a problem either. But again, they're long ways, and that's actually, could pretend loads of potential for mistakes using the cosine rule to find an angle. So the way that I'm going to show you is another way that you can do it. It's something called Heron's formula. Now, Rob actually introduced this to me, and it's when you have three sides of a triangle and you want to find the area. And it means it's adding another string to your bow. It's a third way of doing it, okay? And actually, even thinking about it right now, you could, if you dropped a perpendicular, you could find the height of the perpendicular and do half the base by the perpendicular height. That's fine. Okay, so that's completely fine as well. So there's three ways, but again, you're doing all these side steps. But this last way, it means you can actually get it really, really quickly. It's going to save you a serious amount of time in terms of the maths. And it's called Heron's formula. It's on page 9 of your formula and tables booklet. And what it says in Heron's formula is that A, the area of a triangle, so this is all given to you in the booklet, so A is equal to S times S minus A, S minus B, S minus C. And they also tell you what S is. On the side of that formula, they say S is equal to A plus B plus C over 3. Okay, A, B, and C are just the sides of the triangle. So if I find S now, that's equal to 219 plus 219 plus 230 over 2. So I found that S is 334. If I take that S and sub it in here along with A, B, and C, that's going to give me the area of the triangle. I know they're big numbers, but we're just putting that into our calculator. So in one calculation, we can actually get it. So the area is equal to the square root of S minus A. Now it doesn't technically matter which one is A, so I'm just going to put in 219. S minus B, grand. And then by S again, minus C. Put that all into your calculator in one go, and you get equals to 21,433. Can't read my own writing there. 21,433. That's not the answer to the question, but that's Heron's formula. That has found the area of one face of the pyramid. So one face of the pyramid there. Cool, so Heron's formula. There were these other options, they would have taken way longer. But now if I take that and I multiply by 4 for 1, 2, 3, 4, so multiply that by 4, that answers the question, that's the total area. When I did that, I got 85732. So equals to 85732 meters. And one last piece is they asked it for correct to 3 significant figures. Significant figures are where you go from left to right instead of rounding it off the other way. So correct to 3 significant figures, your answer is 85700 meters. And because again this is area, they should both be squared. Okay, Definitely this is not the only way to do this, and I did this as well with the cosine rule, and I actually got a slightly different answer. I think I was off by about 70 meters squared. That's fine. It's because you're doing a bit of rounding off here. So if you do one of these other ways, you will get a slightly different answer. But for me, if you have three sides of a triangle, you're in the midst of a leaving cert exam, you don't want to be doing cosine rules to go off and get an area, because there's so much possibility for mistake. So we're going to use this Heron's formula again on page 9 of your formula and tables booklet. Has all three areas of a triangle in there. Okay, so all three different types, which is the one we learned from leaving cert, the one we learned in primary school, and now this new one here that's just going to help us out and definitely save us time, Heron's formula. In terms of homework, we're going to build on that. If you look at page 123, the question here is question 13.4. I just want you to try A. This class here was all about pyramids, all about looking at them from above, looking at their square base, which is the ones we saw here, or if they had a rectangular base, pretty much the same idea, and then trying to pick out the piece from it. Remember, the apex is always is directly above the center of the base. Okay, so that's forming slightly different right angle triangles to our last class, but still same again. Pythagoras, SOHCAHTOA coming massively into play for us.